Welcome back, lecture 19 today. So, we shall continue from where we had left in the discussion for gallium arsenide microwave MESFETs. We had ended the last lecture with a discussion on the small signal model, and the natural and the logical progression from there is to talk about cutoff frequencies and what device parameters help you improve the cutoff frequencies. Okay. Although we had discussed the small signal model for gallium arsenide MESFET, as I keep saying, it is more or less the same for even HEMTs, high electron mobility transistors, for gallium arsenide LGAS system or even GaN LGAN system. So, we shall keep referring to these small signal models in future discussions also. The discussions pertaining to cutoff frequencies are also pertinent and relevant almost in the same way for HEMTs and LGAN GaN HEMTs later on. Okay. So, we have to keep that in mind. So, over to the whiteboard here. So, this was the last slide in the lecture 18, where we were talking about small signal model, different components, resistances and capacitances in this small signal model. Inductances are not shown here because inductances become more relevant when you have bigger devices. Why I say that is that any metal line tends to become inductor at sufficiently large length, and you need these wires, long wires or long pads or long metal bars. When you have multi-finger large area devices, inductances become important, especially source inductances. When you wire bond the source, that wire length is sufficiently high, so inductances become important. But for this basic understanding, we do not have to worry about inductors here. Okay. In a real device, a packaged device, a device put in a fixture or a board, inductances are very important. Okay. The model will also have to include inductances later on. So, now the natural thing to actually discuss now is cutoff frequency. So, what are cutoff frequencies? The two cutoff frequencies Ft and Fmax are like holy figures, these are like sacred figures of merit for high performance or high frequency microwave devices. So, Ft represents current gain cutoff frequency. This is the frequency at which the current gain is 1, which means your small signal output current by small signal input current is 1. So, you do not get any gain. Okay. Beyond that you do not get any gain, this is the limit. At frequency lower than this, you are going to get some gain, current gain. So, of course, like any other many of the things that you have studied in your undergrad electronics, your gain, whatever you represent this with, if you plot it frequency in log semi-log scale, you will have the gain actually fall with frequency. Okay. And there is a slope, there is a 20 dB per decade slope after hitting a pole, but the gain will follow with frequency, and physically and this is true for any system, but in this particular transistor, in the case of transistor with higher frequencies, your carriers are not able to cope up as much. So, physically an intuition is that at the higher the frequency you go, the carriers, the electrons that are moving are not able to deliver you as much gain. Okay. You can always use the concept of poles and zeros and mathematics to explain this, but physically this is what is happening. Okay. The lower the frequency, you are changing the signal slower. The carriers have all the time to go from one point to another point, your gain intuitively speaking is high. The higher frequency you go, eventually the gain will become 1, or log of the gain will become 1, or log of the gain will become 0 dB. So, at that point you are such a high frequency that the carriers are not having enough time or the scope to come back and forth, your gain becomes 0 dB or 1. Okay. That also reminds me that in microwave engineering concept, dB is very important. Okay. In case it is basically like a gain or a ratio, dB is actually a gain or a ratio. Okay. And what it means is that if you are talking about power, then this is 10 log of that ratio with respect to 10. If it is a current or a voltage, then you are talking about 20, okay, log of that ratio by 10. So, if I say a current gain of say if I say current gain of 10 dB, this is a current gain. If a current gain is 10 dB, that means 20 log of the gain is this. So, this is 2. So, 10 to the power 0.5 or square root of 10, your actual current gain is square root of 10. Okay. This is current gain. If it is power gain, if you say the power gain is 10 dB, that means 10 into 10 log of the power gain. So, power gain, okay, is 10 to the power 1, which is 10. So, you have a power gain of 10, okay, for a 10 dB. All right. This is very important, and so this is Ft. I will come to that quickly, and this is current gain cutoff frequency. Fmax is like which called maximum oscillation frequency. Now that is a little bit more complicated. This represents a maximum oscillation frequency of 1. It basically means that your power, now maximum oscillation frequency is the definition. Fmax is defined as the maximum oscillation frequency where the power gain is 1, you can say like that, where the power gain is 1. So this Fmax is a more critical and relevant figure for microwave power devices. Ft is a more relevant figure for like high speed digital devices or in general even for low noise devices. Okay. So power gain becomes 1, that is Fmax, current gain becomes 1, that is Ft. They are related in some way but they are not identical. Okay. And one thing is understanding the concept which we are going to discuss now, we are discussing now, and the other thing is to actually understand how these are measured. How is Ft and how is Fmax measured? That part we have to discuss towards the end of this course, after we finish BJT, HBT, HEMT, LDMOS etc. Towards the end where we have a module on microwave engineering concepts. At that point we will discuss how to de-embed, how to actually extract this, because we need to understand the concept of S parameter, Y parameter, H parameter, 2-port linear network analysis. Some extent we need to understand that, not detailed mathematics, we are not going to do any matrix operation, but we need to understand the basic concept. Then we will be able to appreciate it semi quantitatively, oh this is how this is measured, and we have to see the images or pictures of how, what are the measuring instruments, the vector network analyzer or the how a RF probe station looks like, how you are going to measure that, those things are also important, but here we are just introducing the concept. So Ft is where current gain is 1, Fmax is the frequency where the power gain is 1. Okay. Ft is more straightforward to analyze, Fmax is little bit more convoluted, more complicated to understand, but nevertheless we will go through that. So if you talk in a very simplistic way, okay, if you talk about very simplistic way for current gain cutoff frequency, if you talk about small signal model, okay, if you talk about small signal model, you have it could be any transistor, it could be HEMT, it could be MOSFET, FET, MESFET etc. Okay. If you have a gate here and in a FET the gate of course is insulating, there could be barrier or a gate Schottky gate, and it is almost insulating, very low current is coming out here. So the resistance, or I would say the impedance of the gate here in small signal would be actually 1 by j omega c GS. If I ignore the gate drain capacitance, it can be ignored in many cases. If I only consider the gate to source capacitance, then 1 by j omega c GS is the impedance, it is the input impedance actually. Okay. So now what is current gain? Current gain is output current by input current. So I can say output current divided by input voltage into input voltage divided by input current, correct. Now this output voltage by input current actually is this is actually nothing but the output current by Vg, the output current by input voltage, it is basically Gm. Okay. Small signal fine, not DC, but that is okay, it is a representative of Gm, and V in by I in, actually the input small signal voltage by the input small signal current is precisely your input impedance, which is your 1 by j omega CGS. Okay. And it has to become 1 at cutoff frequency is Ft, so omega t. So it basically means if I take the magnitude only, because I want to remove the j, then omega t into CGS is equal to Gm. Omega t is nothing but 2 pi Ft, the cutoff frequency, into CGS equal to Gm. So your cutoff frequency Ft is basically Gm by CGS. Of course there is a 2 by factor, but that is okay. Gm by CGS is your cutoff frequency, very important. So to improve the cutoff frequency, your Gm should be high and your capacitance should be low, but it generally does not happen always like that. If your Gm is high, naturally your capacitance also becomes high. So that because this ratio actually represents the velocity, and this velocity of a material is constant at the limit of saturation. So this ratio of Gm by CGS you cannot arbitrarily increase. Now this entire analysis is based only on the intrinsic device, which means I have ignored all the parasitic components, I have ignored all the source resistance, the drain excess resistance etc., which is not correct, but for only for the intrinsic device this is how it is. So the Gm by CGS ratio decides your cutoff frequency, the current gain cutoff frequency. A high Gm helps you in improving the cutoff frequency. A low CGS helps you in improving the cutoff frequency. But this is the intrinsic device. You know what this intrinsic device is? Intrinsic device is precisely the device below the gate. So, if this is your gate metal, okay, this is your channel, this is your intrinsic device, this is your drain which is outside the device, this is your source which is the outside the intrinsic device. You have source access resistance, drain access resistance, those are extrinsic. If I only talk about the intrinsic device, this intrinsic device has a length of gate length Lg, and at the maximum speed you cannot exceed more than velocity of saturation. Okay, if you can call it the peak overshoot velocity for gallium arsenide, if there is a overshoot of velocity, that is fine, but Lg, the gate length, divided by Vsat, this is the time taken by the carriers to go below the gate. This is called transit time, the gate transit time, and this time, this transit time is the minimum delay that you will have in your device, even if all your parasitics and extrinsic components are 0, hypothetically speaking. But the intrinsic delay, this is your intrinsic delay. Intrinsic delay is basically the delay that comes because the electrons take a finite time to travel below the gate. Okay. The electrons take a finite time to travel below the gate, and that is precisely given by the gate length divided by the velocity of saturation. This intrinsic delay is the minimum delay that you will have in your device. You cannot have a delay lower than this. Okay. So, intrinsic delay is Lg by Vset. Now, the total delay is, of course, to this you have to add parasitic delay, extrinsic delay, etc. We will come to that very much, of course we will discuss that in this course, but in this particular context now the transit time is this, okay, and this is for the intrinsic device only. All the extrinsic elements, all the parasitic elements are ignored. This is the minimum delay you will have, and the cutoff frequency is 1 by 2 pi the transit time. So, cutoff frequency will become Vsat divided by 2 pi the gate length. Okay. So, your cutoff frequency is Vsat by 2 pi gate length. This is your intrinsic cutoff frequency. You cannot get a frequency cutoff frequency which is higher than this. This is the upper limit, and this is equal to Gm by Cgs in a way you can say. Okay. This is equal to Gm by Cgs. So, in a way, if your gate length becomes short, your cutoff frequency improves as long as your parasitic components do not dominate. If your parasitic components dominate, then your gate length being shorter will not help so much. So, which means your parasitic components also have to come down. With shorter and shorter gate lengths, the parasitic components become relatively more important. So, your parasitic components like contact resistance, drain access resistance, etc., has to come down more significantly as your gate length becomes smaller and smaller. Saturation velocity is fixed for a material, but if you choose a material of a different type where the velocity is fundamentally higher, then you are going to get higher cutoff frequency. For instance, you will see in L-gas gas HEMT, okay, if you introduce an indium gallium arsenide channel in gas, fundamentally the carrier velocity is higher in gas. So, your cutoff frequency will naturally be higher. Okay. So, that is your material engineering. You can choose a different material, but again there are many problems, lattice mismatch, misfit dislocation, etc. So, well, material, if you choose a material with higher velocity, you get higher cutoff frequency, or you can reduce the gate length, but eventually your Gm by Cgs is all that matters. This is exactly Gm by Cgs, by the way. Okay. So, this is your current gain cutoff frequency. This is measured from S parameter scattering parameter measurement in a vector network analyzer. The theory of two port network analysis will come at the end, towards the end of this course. This is fine, this is cutoff frequency. However, if you consider the entire device, you consider CGD, the gate drain capacitance, the source access resistance, the drain access resistance. Again, the output current does not saturate. So, there is an output conductance RDS, there is an output conductance there. If you consider all of them, then there is a more elaborate and bigger expression for cutoff frequency. Okay. How do people derive it? Well, people derive it by going to the small signal model, this, and then from the small signal model you can derive it. So, essentially you have to measure this scattering parameter, S parameter, they have to convert to Y parameter. These are some two port network analysis. Then you have to go to H parameter, hybrid parameter, and you define the gain as H21, which is your small signal gain, and to find out the gain, essentially you have to do the output short. The drain and the source has to be short. You short the output drain and source, and so you will shunt out lot of capacitances there. Then you find out the output current that is flowing here, I out, and the input current that you are giving, I in. So if you do an I out versus I in and you apply Kirchhoff's law or whatever throughout the circuit, you have all these different components, right. So eventually you will get I out by I in as a function of all these components, and you set that equal to 1. So you will find out the capacitance because the cutoff frequency, because all the capacitances will have a 1 by j omega c dependence, no. So omega brings you the frequency anyways, so you set equal to 1, you get a gigantic expression for Ft, and that precisely looks like this. Okay. If you are talking only in the intrinsic, then it is basically Gm by Cgs, Cgs plus parasitic capacitances also come. This Cgs by the way consists of Cgs plus Cgd, gate drain, gate source. I conveniently ignored gate drain, but you can include that. This is what I told about. Okay. This is a more gigantic expression where you have the Gm, you have the gate capacitance which is Cgs plus Cgd, you have drain excess resistance, source excess resistance, output conductance or output resistance. This is gate drain capacitance, this is transconductance, this is drain excess resistance, source excess resistance, this is parasitic coupling between the source and the drain gate metal. I ignored the gate drain capacitance, but you can include that. So Cg essentially is gate source plus gate drain capacitance, and C parasitic is the parasitic coupling between the source and the gate metal. And so you can see that the actual expression for cutoff frequency has all these terms, the drain excess, the source excess resistances, the output conductance, etc., etc. So for improving the cutoff frequency, you need a high Gm, you need to minimize the source and the drain excess resistances, you need to also minimize your output conductance, which means your RDS should be as high as possible, which means your current in the output characteristics ID versus Vd, it should saturate, it should not go like this. Okay. So that will help improve your RDS, and you have to lower your gate source capacitances, gate drain capacitances. There are many ways. For instance, I told you if you have a mushroom gate like that, your gate to drain capacitance increases, not good for Ft but good for breakdown. So that is a trade off you have to pay anyways. So this is your gate drain capacitance. People use field plates that also help improve breakdown, we will see, but also helps sacrifice your or you mean to say your capacitance has increased, so your cutoff frequency decreases. Okay. So shorter gate length, very important, LG has to come down, your GM has to improve. You need a material with high electron mobility for sure, high electron velocity also. Lower excess resistances, I told you, for that you need to scale the device, bring the device dimensions shorter. Reduce parasitics, which means lower contact resistance, the contact resistance should be as low as possible. Now for Fmax you need a low, I will come to Fmax very soon. This is your expression for Fmax. Fmax is the maximum oscillation frequency, is the frequency at which your power gain is 1, and that is also has a very gigantic expression, and simplistically it can be approximated as this square root of Ft divided by something something. Something something here is the gate resistance Rg and the gate drain capacitance Cgd, alright. So of course for higher Fmax you need a higher Ft, straightforward. However, you also need a lower Cgd, gate drain capacitance, which anyways we need to lower because your Ft depends on that. The new thing here is Rg, your gate resistance has to become as low as possible. Gate resistance does not influence Ft, does not affect Ft, okay, but it is significantly affecting Fmax. So your gate resistance has to be lower as much as possible, and that is why you have the mushroom shaped gate. Remember the mushroom shaped gate we talked about, we showed here, yes, this precisely this lowers the gate resistance Rg, okay, this precisely lowers the gate resistance, it helps improve Fmax, okay, it helps improve Fmax, but it also increases Cgd, and it may not be very good for Ft, not so good for Ft, but you can still live with it. It is not like your Ft will be killed, your Ft will marginally reduce, but your Fmax will improve significantly. So this is your mushroom gate. If you want to get a record Ft, then you need a rectangular gate, which means you do not want this, you just want a gate like that, that is a rectangular gate that gives you record Ft but terrible Fmax in depending on the design. Okay. So this is the expression for Fmax, your gate resistance is very important. And how do you measure Fmax? Again you need to measure S parameter, scattering parameter in VNA, but unlike in Ft where I said that you have a gain which is basically your H21, we will come to that and it is like a scattering parameter, but it is a hybrid parameter, and you plot H21 and you measure till certain frequency, then you extrapolate. Where is the point where it goes to 0 dB. 0 dB stands for 1 gain, 20 log 1, that is your FT. Okay, it goes as a 20 dB per decade slope. What it means is that it falls by 20 dB for every 10 times increase in frequency. So if I go from 1 gigahertz to 10 gigahertz, that is a 10 times increase in frequency, the gain will go by 20 dB. So if this was 35 dB, okay, it will become 15 dB here. Ideally there could be small variation depending on the actual device, but 20 dB per decade is the current gain slope that comes, and you extrapolate and then you find out this is the cutoff frequency. Fmax is little bit more complicated because Fmax is power gain. Now the power gain definition becomes a little bit more tricky. There is a maximum available gain, there is a maximum stable gain. Okay. The definition of this depends on the stability of the device, and that we are moving to the domain of RF circuit design, which we will try to avoid. A device, an amplifier needs to be stable. Okay. What it means is that whenever you have a transistor, your output can also feed in signal to the input, and it can come back amplified from the input to the output, again it will go back, it will come out. It can lead to an oscillation, and that is bad for an amplifier, and if it leads to an oscillation it is unstable. So you need to have a stability, and stability is defined mathematically by something called a K factor, and that is experimentally you can measure it from S parameter, again scattering parameter. So K factor will tell you whether the device is stable or not, and there is something called unconditionally stable, okay, and there is something called conditionally stable. So there are different categories there. Now the thing is, if you have a device, there is an output, there is an input, there is something called matching, the impedance has to be matched. Okay. These are things that we will discuss towards the end of this course about impedance matching, but if you are matching it to an optimal stability, to make sure that this is unconditionally stable, okay, then you call it a maximum available gain. If it is stable only at a certain point, okay, and then we call it maximum stable gain. So there are different things. If you plot this power gain, this has different expressions by the way in terms of S parameter. Initially it will be like MSG, and then it will be MAG. The maximum available gain falls faster, maximum stable gain falls slower. I think it is 20 and 10 dB per decade, okay, and this demarcation is dictated by the K factor by the way, which side is conditionally stable, which side is not conditionally stable, etc. So the definition of Fmax becomes whether you should take this or you should take this becomes a little bit more confusing. So what people do is that people plot something called unilateral gain, or it is called Mason's unilateral gain. It is the expression of a gain, power gain, which is fairly independent of this complexities of stability, okay, conditional unconditional stability. It's so the U is plotted, power gain U is plotted, and that U intercept at 0 dB for power gain is taken as Fmax. But people still plot the MSG MAG to find out how close it is to the U, because that is the nomenclature, So U is the unilateral gain, and this is again measured using S parameter, scattering parameter. We will see how these are measured by the way, okay, but the unilateral gain is measured and it comes an intercept, that is your Fmax, and this Fmax depends on the gate resistance by the way. Both FT and Fmax are very important for a device, okay. Now that we know all of these things, there are two important application of a gallium arsenide MESFET. One is for power amplifier, where you have a small signal that you amplify to large signal, and then you have a low noise amplifier where you want to amplify a very weak signal, but the noise is more important there more than power, okay. So first we come to power amplifier. For a power amplifier, again power amplifier design is a different topic and ball game altogether, and there are a lot of things that depends on the way you bias the device for power amplifier. But to a first order, what are the different requirements for a power amplifier? You need good output power. For a good output power you should have a high breakdown, because higher breakdown means that you can bias the device at higher voltage, and that will give you higher power. You need high current. Of course the product of breakdown voltage and current decides or dictates how much power you will get. The heat should be managed, because the more power you get, the more your device will heat up, and if your device heats up, your mobility, velocity, everything will degrade and your current will come down and your device performance will be suboptimal. So, heat management is extremely crucial. There should be no current collapse. We will see what current collapse is, but in general your DC current and your RF current could be very different because of traps. The traps can lead to a collapse of the current and that should be minimal. Okay. These conditions are required for getting higher output power in any FET, whether it is L-GaN hemmed, whether it is L-gas hemmed, whether it is gallium arsenide MESFET, okay, whether it is silicon MOSFET, does not matter. High gain. For a power amplifier you need a good gain, because if your gain is terrible then you need to cascade many stages of devices to get gain. Your particular subsystem or a front end module or some kind of circuit might need suppose 35 dB gain. Each transistor can give you suppose 12 dB gain. That is bad, because then you have to put 3 transistors at least, okay, 12 dB, 12 dB, 12 dB. So, the whole thing will give you 35 dB gain. That makes it more complex, you know, the circuitry becomes more complex, real estate or the area also increases, noise also will increase because you are adding subsequent stages, and it is not a good thing. So, your higher gain is desirable in a power amplifier. For higher gain you need a higher GM. A good GM always gives you good gain, and for a good GM you need better carrier confinement. The gate channel distance has to be low, the gate channel control has to be really good, no carrier spillover, no short channel effect, etc. Short gate length, an LG being short helps improve the gate length. Of course, the source drain spacing also has to come down, and then you need a higher efficiency, and this is particularly important for handheld electronic gadgets like smartphone, cell phone, iPads, or all this anything that you carry in your hand or anything that operates on battery, because power amplifier is that component in a gadget or in a device such as a smartphone which consumes the highest amount of energy and power. Okay, power. So, your battery, the lifetime of your battery, how long your battery can sustain before it drains out, is largely dictated by the power amplifier. I will have to repeat this statement. Power amplifier is the most power hungry block on any battery operated device, smartphone, anything, drone, anything. The power amplifier takes away most of the energy, most of the power. So, your power amplifier is an extremely important component, okay, extremely important component. And because the power amplifier boosts the power and sends it to the nearest through the antenna, it will send it to the nearest base station or cell phone tower. So, in order for that transmission on the transmission chain, you have the power amplifier to amplify the signal from your cell phone and send it to the nearest base station. So, the power amplifier has to consume the maximum energy. The efficiency will directly determine how long your battery lasts. So, because you cannot arbitrarily keep increasing the battery size and battery capacity, because a cell phone will become larger and bulkier, that is not what you want. So, a efficient power amplifier helps you increase the lifetime of the battery. There are different efficiencies, the most important here is power rated efficiency. We will come to all these terms later on, but in general power rated efficiency depends on gain. So, you need a high gain, you need a high GM. However, power rated efficiency also depends on something called drain efficiency, and drain efficiency is basically how much RF output power you are getting divided by how much DC power you are supplying. So, the DC power you are supplying is kind of constant. So, the RF output power that you get becomes higher when your input RF power also becomes higher, which means you should be able to put in more input power to be able to get higher output power for a constant gain, so that your this term which is called the drain efficiency increases, in which case your overall power rated efficiency also increases. Now, this efficiency is a complex interplay of not only this ratio, but also the bias condition. In what biasing condition are you using the device? So, there is class A, class B, class C, class D, etc., different categories of biasing the transistor for power amplifier. So, those will also dictate significantly how much efficiency you get. Input power, I already told you, higher input power gives you higher output power, gives you higher drain efficiency, and input power, bias condition, and device geometry, by the way, how many fingers you have, what is the gate drain spacing, what is the total device dimension, what is the total parasitic, what is heating, everything, it is a complex interplay of all of these things will dictate efficiency. Okay, it is not a singular thing. So, it is you cannot quickly point out what will improve efficiency, it is a complex interplay of many things. Okay. So a wide bandgap material such as gallium nitride probably not probably will for sure be able to give you higher breakdown voltages for a similar dimension than a gallium arsenide MESFET or a HEMT. Okay. So inherently the efficiency of gallium nitride will be higher, because if you want to do an apple to apple comparison and have the same breakdown voltage for a gallium arsenide MESFET and a GaN HEMT, then your device dimension for gallium arsenide MESFET will be significantly large to accommodate the same current and accommodate the same breakdown voltage as an equivalent gallium nitride HEMT. So your overall device dimension increases, your parasitic increases. Okay. So overall your efficiency will drop. So there are just different things that come into picture. It's not very simple. Now if you want to extract power at say some frequency f, at that frequency you want the power amplifier to give you power, then the cutoff frequency ft fmax loosely should be kind of 5 times more than that. So your ft your gain is dropping like that, right? This is your ft and maybe this is your fmax, very close. Okay, this is some frequency. You are going to get a power of 1 there or a gain of 1 there. That is not where you want to operate. You want to operate here. So wherever the highest frequency that you want to operate here should be at least 4 to 5 times, I would say, lower than the cutoff frequency. So if you want to power at X band, which is 10 gigahertz, cutoff frequency of 50 gigahertz would be excellent. But people, you can have a cutoff frequency of even 35 gigahertz and you will still get some gain, but it may not be as high as gain, but you might still get a gain. You will still get a gain, not you might, you will get a gain, but it may not be very high. If you have a cutoff frequency say 100 gigahertz, or then your gain will be very high at 10 gigahertz. However, 100 gigahertz of cutoff frequency is probably an overkill. You do not necessarily need such a high frequency. 40-50 gigahertz is good enough. So because to get 100 gigahertz cutoff, your gate drain spacing has to be really short and your breakdown will be low. That is not something you always want. So there is all these trade offs that come into picture. Okay. So with that, maybe we will end the lecture here today on we are introducing power amplifier. We are not introducing power amplifier, we are introducing device for power amplifier. What are the requirements for a field effect transistor to enable a good power amplifier is what we are discussing. This course is not about discussing power amplifier. Okay, please remember that. So going ahead in the next class, we will define what the figure of merit is for such kind of devices that go into power amplifier. We will also discuss about how to manage the heat, for instance, how to get higher breakdown, higher current. We will touch upon briefly about air bridge, via hole, etc. technologies, but not in so much detail, because in subsequent HEMTs and other MOSFETs lectures we will go through that in more details. Okay. But this is very important. Whatever we are discussing here are relevant almost in a similar way for other kinds of field effect transistors also, especially for 3-5 material. Okay. So thank you for your time. Next class would be the last lecture on gallium arsenide MESFET, which is a lecture 20. Thank you for your time.